Hello again, everybody, and welcome back. This is example 11.8. Should say 8, not 7. There's another thing I'm going to have to fix with this problem as well, aside from changing that to an 8, and that is the fact that this is missing one bit of information. So let me fix that for you, aside from fixing the 8, and then we'll go ahead and get started on this, all right? So let's read this real quick. We have a coin that we place on the turntable that is like a record, okay? So it's this flat plate that is spinning around. And you can adjust the speed so that it spins faster or slower, all right? What it doesn't give you, however, is the coefficient of friction, the coefficient of static friction. And for this problem, we're going to make that 0.35, okay, 0.35. And so the question is, how fast can you spin it? What's the largest speed, or I can't really say velocity, but speed, such that the coin does not slip off the record? All right? So let's go ahead and see if we can sketch this and make some sense out of it. All right? So here's our, oops, let's do that. All right, so here's our record kind of on an angle like that. And that's not a bad ellipse right there. And right here is the center, okay, where the little pin is, the middle of the record. And our coin is, I'm going to draw that in gray. That's going to be right there. Okay, so the record is sort of spinning around horizontally. And that distance is 15 centimeters from the center of the turntable. Now, this right here, first of all, what's the first thing you say? We need to convert that to meters, right? So that's our radius, and that is 0.15 meters, because with centimeters to meters, you move the decimal point 2 places to the left, okay? So that R right there, 0.15 meters. Got it. So the question is, what is the speed, the largest speed that we can have so that the coin does not slip off? All right, so in order to do this, we need to write some general equations. I'm going to take this and I'm going to shrink it down a little bit so it's kind of up out of the way. All right, kind of like that. And so for part A right here, let's ask ourselves, what are the forces that are involved in keeping this little coin right here stationary, not slipping off the turntable? And in fact, I should probably make this a little bit bigger right here, because I'm going to need to mark that up, and then we'll make it smaller again. All right, so there is a centripetal acceleration. Oh, by the way, you may be saying to yourself, well, wait a minute, we don't even know the mass of the coin. We don't know the mass of the coin. Well, when you see that, and assuming the problem is written right, it means you shouldn't have to worry about it, okay? And we'll see why in just a second. First of all, what is keeping this coin at a certain distance away from the center right there? Why is it not sliding off? There's no string attached to it, right? There's no little wall here on the outside holding it in place. The only thing holding it in place is the static friction force. All right, static friction. And so we can say that the net force, and let's see, I'll shrink this down here a little bit more. All right, that the net force on the object is the static friction force. Well, the net centripetal force on that is the static friction force, which we can also write in more detail, right? How do we find the static friction force? Let me go back to this for a second. All right, well, that static friction force is going to be what? That's a coefficient of static friction times what? Usually times the normal force, which is the same thing as mg, right? If mg is straight down right there, the normal force is directed upwards. It's a supporting force, all right? So it's really the static friction, or the coefficient of static friction times mg. All right, good. So let's go ahead and write that as our definition of our coefficient of, or our static friction force. Coefficient times mg. Now, once again, m is what? Well, it's the mass of the coin, which we don't know, but that's okay. All right? Well, what is the other way we can state centripetal force. If we think back to Newton's second law, we can always state it in terms of mass and acceleration. So the net centripetal force directed toward the center is this component force right here, caused by friction. It's also mass times centripetal acceleration. All right, so what's it really asking us for? It's asking us for the speed or velocity that the coin has. All right, so can we restate this centripetal acceleration in terms of velocity? And I think you know that we can, right? That equals mass times, how do we state centripetal acceleration with respect to velocity? That's v squared over r, right? V squared over r. So this right here and this right here we can set equal to each other, right? Because they both are descriptions of net force, okay? So we can say coefficient of static friction times m times g equals mass times v squared over r. So why does it not matter what kind of coin it is or what kind of any object it is? Because the mass is going to cancel out. That goes away, and that goes away, which means we should be able to solve pretty easily for our velocity. So to solve for our velocity, we're going to multiply the r up. So, oops, I'm going to keep it in blue here. We're going to say our velocity equals r coefficient of static friction times g, right? But in order for it to be velocity, not velocity squared, we needed to square root that, right? So there we go. There's our general equation. Now all we need to do is simply plug in values. If you had started plugging in values up here, let's say you knew the mass for a second, you started plugging values in, it would have gotten more complicated because you would not have realized that those masses cancel out. Stay with general equations as far as you can or until the very end, and then plug your values in at the last minute. So what is our radius? Radius is 0.15 meters, okay? Coefficient of static friction, that's 0.35. And there's no unit for that. And of course, g is 9.81 meters per second squared. If we do that, that'll give us the maximum of velocity such that the coin does not slip off. Anything beyond that, and there won't be enough centripetal acceleration to keep it on, or there won't be enough static friction to keep it on, and it will slide off. All right, so 0.15 times 0.35 times 9.81, and we'll take the square root of that. Trying to write with my laser again, 0.718 meters per second. And there we go. There's our velocity. There's our, or I should say our speed. Our speed at any one point, or velocity at any one point right here. The speed can be any direction, but the velocity has to be in a given direction. Okay? So that's it. Now I'm looking at part B right here. This is going to be the same thing. I feel like for part B something was left out. So, we're not given a rate. All right, we're not given a rate that is or a frequency. So, don't worry about it. All right, I need to go back and fix this problem apparently. So, but this is a good example of drawing free body diagram, solving using a general equation, plugging in, and getting your answer. All right, thanks for following along. I'll see you on the next one.